Hey, welcome back to the lab. 10 short days ago, I promised you hardware. I promised you prototypes. I promised you time in the lab. Yeah, let's talk about that. Did I scare you? Did you really think that we'd burn 10 whole days and accomplish nothing? Really? Nothing? Come on, not EE for everyone. We are all about projects. We're all about getting stuff done. The last time we talked about prototypes, I had a laundry list of things, or small pieces of the UPS, that we really wanted to test before finishing the circuit design. In a broader sense, we've already talked about 3 of the 4 power modules, but really, the design framework is mostly in place for all 4. I'm keeping my cards, whatever. There are some details to work out, like microcontroller selection, and maybe some minor tweaks to the hardware after we finish our analysis and testing of these subcircuits, but the big blocks of important circuitry are there. Isn't that exciting? Here's what we got done since we last talked. We made some bills of materials, or BOMs, and their list of components that are used on a circuit board, or PCB, alongside how many of each of these parts are needed to build the whole design. We exported a bill of materials, or a BOM, from each of those 4 schematics. That's the mainboard, inverter, battery, and PFC. And this is where I dove into the matrix with filters in Excel. I used a few key equations like VLOOKUP and match to find every unique component. Basically, if the same part shows up in all 4 designs, we only count it as one part. We then needed to merge the quantities from all 4 bills of materials into a master BOM. Now, this master BOM is a list of how many parts and which parts we would need to build all 4 power modules. For a lot of parts, like transistors, ICs, those need to stay no matter how many are used. Like, they were selected for a purpose, and maybe that purpose is only one circuit, but it's an important circuit. That's why it's there. Not always the case for passives, or resistors and capacitors, though. In my limited wisdom, I may have elected to use a 1K resistor, a 1.27K resistor, and a 1.15K resistor, all in 3 different designs, when one value would have worked fine for all 3. I find that I tend to scale powers of 10, so like I'll use a 5.11, and if I've already got a 5.11, then I'll use like a 5.11K. Like, I like to stay with the same 3 numbers. I don't know why, so I just need to like consolidate these down into less values. Because for something like a 1K, a 1.27, and a 1.15, one value would probably work fine for all 3 of those, but yeah. The easy way to think about this is that I don't want to buy 300 different values of resistors and waste a bunch of money, because wasting a bunch of money to buy 300 different values means that we'll waste a bunch of time dealing with sorting 300 values. I don't want to deal with all of that. So how can we fix this? Basically, we needed to pull out one of our critical skills, and that's BOM consolidation. BOM consolidation is essentially flagging parts that are only used once, twice, or a few times throughout a design. Once we know what parts aren't commonly used, we can decide if a more popular part can be used instead. Great, right? So if we've got a part that's used twice in the whole design, and we've got another part that's really similar that's used 100 times in the design, maybe we should use the one that's already used 100 times, right? This limits the number of parts that are unique and that are needed to build the system, and that reduces cost no matter how many units are being built. And basically, it reduces complexity and makes things better in every possible way. If I could build a schematic with just one resistor value, believe me, I would, but unfortunately, that's usually not practical. There are power limits, voltage limits, current limits, and physics sometimes demands different component values. So rather than choosing only one resistor value, I did the next best thing. I selected as few unique resistor values as is possible. Once we picked these values, the values that are required to make the design work, I selected an orderable part to build my schematic symbols for. This practice of actually building a schematic symbol linked to an orderable part number can save a lot of headaches down the road. It becomes like a self-documenting bill of materials generator. If this mapping is perfect, if the mapping from 1K resistors in our schematic to 1K resistors in the real world on the board is perfect, we can avoid a lot of problems. If we accidentally map 1K resistors in our schematic to 100 ohm resistors in the real world, that could be a problem. For capacitors and resistors, we consolidated part values on the 4 schematics We then updated the symbols to have orderable ones, getting rid of the placeholders, which was great. It's easy, but at the risk of asking a silly question, why exactly did we update the 4 schematics that we're not about to build instead of just updating the prototype, right? That seems a little backwards, right? Believe me, I didn't just do it for fun. I did it for a reason. If we update the master schematics and copy the critical blocks out of them, if we copy the critical subcircuits out of the real design and into our prototype board, we will know that the prototype we're testing is exactly the same as what we're about to build for our final design. That's important to me because if I find issues during our testing, it's absolutely critical that the corrections that our schematic updates find their way back into those 4 key elements of our design. Having a working prototype and a broken UPS is not what we're trying to accomplish. Okay, so we reduced the number of unique parts to a minimum, updated the 4 schematics, and now what? Well, we took the inverter, PFC, mainboard, and battery backup and smashed them together to create the complete DC power architecture. The power architecture that will be spread between daughter cards, power modules, through PCIe connectors, put it all on one board. The high power, high voltage architecture is really simple, and I don't feel like I really need to prototype that because it's expensive and it's simple. It's basically, you have 2 high voltage power supplies, diode ORed together, and an inverter that takes that and spits out AC. So as long as my diodes are pointed the right way, we'll be fine. The DC architecture is a lot more complex. We have more voltage sources, a complex power path with 3 possible sources for the 24-volt bus, all kinds of stuff hanging around, not to mention the high accuracy, noise sensitive analog circuitry that's all smashed together with our power supplies. Yeah, I want to test some of this stuff out. For example, I don't know if you noticed, but I noticed that while we were testing things like voltage regulation and how sinusoidal the output voltage was on our first UPS, I saw that the temperature monitoring appeared to be, well, terrible. Read 4 different voltage sensors, get 4 different values, and I noticed an error of at least 7 degrees when comparing 2 of these temperature monitors side by side, and they were both the same temperature. That is not great. And we never really had the hooks in our first UPS to investigate whether the issue was the ADC, the voltage reference, or the actual temperature monitor IC. So just put down a copy of all of those circuits so that we can find out where the change is required and make it. Reset circuits, fan control, fan monitoring, analog references, it's all here. All the little DC circuits that should be a slam dunk are cheap, but if they don't work, nothing will work. We have the complete low voltage power architecture in these supporting circuits as it will be with the 4 modules assembled and the simple but untested circuits that either didn't behave exactly right in the previous design or just that we want to test to avoid issues down the road. What else? I copied the serial communication schematic down and implemented an RS-422 transceiver with a simple DB9 cable so that we'll be able to loop back serial data from an FTDI header into another one back into a PC. So we can use a tool to shove lots of serial data through the COM port and then record the response in the other COM port, check for things like failure rate of our serial communication, test retransmission algorithms, take a look at signal integrity or the signals passing through our cable. Now that's great, but as long as there's still some room on our PCB, I think I want to get up close and personal with the new voltage and current measurement systems being implemented on the inverter module. I want to understand exactly how this thing works. I want to know the phase delay. I want to know how accurate it is. I don't want to need to use trim pots in our design again. We're using a new isolation amplifier since 5 kilovolt isolation now required, so there's a little bit of risk there and I want to burn that down, and a new current monitor as well due to the higher isolation requirement. Pulling these circuits into our prototype allows for testing these analog monitoring functions for accuracy and noise rejection without the fear of high voltage or electrocution. That makes things a little easier. Now I'm sure that you've noticed, but there are callouts all over this schematic to show where designs came from. This is just to make it easier for me to remember when mistakes are found and updates need to be made in the source schematics. Normally I'd use a similar method to label subsystems or subcircuits anyways, but being very careful that everything is labeled with what it does and where it's from is a great idea for this prototype, given that there are 4 schematics that any individual circuit may have come from, or it may be used across schematics. So it's important that we keep this traceability. We're almost to the fun part, I promise, But let's talk about the power architecture in just a little more detail first. This prototype will be able to charge batteries, discharge batteries that provides the 24-volt backup to the digital systems on the UPS, detect power failure on the primary DC inputs, and hopefully we'll be able to build this all into something that will successfully switch over from the primary DC inputs to the battery backup before the microcontrollers reset. My fingers are crossed, but this failover, the power path transfer that literally keeps the entire system alive, yeah. I want to test that before we spend a bunch of money building a new UPS. If the big expensive power supplies work, but the 5-volt power supply doesn't have enough bulk capacitance, I'd rather know now. So that's what I really wanted to highlight from like a progress and schematic and everything else update. That's really the bulk of what we got done, and it's the really important stuff that we got done. So why don't we just kick back for a moment and have some fun, yeah? So we ran and fixed the design rule checks in the schematic, exported a netlist BOM, and started laying out our prototype. This is all in KiCad. Started with a 4-layer board, but I found that we didn't really need it, so I went ahead and reduced that layer count to 2. 2 jumper wires are required to accommodate the shift from a 4-layer board to a 2-layer board, but this was a small price to pay. Literally, this was a small price to pay. 5 prototype PCBs cost only $50, delivered. What a time to be alive. Moving on up then, after a few short minutes, or long minutes, I guess, depending on how you count minutes, we got this awesome proto board finished. Yeah. I know this might be a little awkward with the silence and all, but can we just bask in the 3D rendering, okay? It's been a long time coming. I just want to enjoy this moment. Awesome. Yeah. The prototype is all done. We're ready to buy this thing. So all we had to do now was quote the board on PCB Shopper, found that JLC PCB was the cheapest for what we needed, and we moved on forward. I like JLC PCB. I've used them a few times before on the Plant Light project, the inverter prototype, and I like what they do. 2-layer, 4-layer, I've had great experiences with them so far. Here's hoping that today's no different. Not sponsored, by the way. Just so you know, I like to recognize good work when I see it, and man, from what I've seen, JLC PCB delivers a really great value for people that are building things like this. Okay, last steps time. I took the BOM for the prototype board, loaded the parts into Mouser and DigiKey. Some of these are only available from one or the other right now, so we ran the BOM through both and bought everything from where it was the cheapest. Hopefully our Excel filtering skills were on point. Everything got ordered, and we'll be able to have a lot of fun in the lab very soon. Keep an eye on our channel on Saturdays specifically, because we're going to be live streaming a lot of circuit testing, debugging, soldering, just generally hanging out in the shop together. I'm really excited to see how many of our designs turned out well, and I'm really looking forward to learning a whole lot more. If you like what you saw today and you're excited for these prototypes, subscribe to be notified of our future videos. We're about to discuss the updated battery charger design and break out CAD with our 3D printer to revisit and finally finish a great way for us to keep all of these small parts organized and stored. If you want to support the channel, consider checking out the products that we featured today through our Amazon affiliate links in the description. It really helps us out a lot. I think that this prototype will be great. If you're excited too, let me know by hitting the like button on this video, following us on Twitter, or leaving a comment letting us know what you enjoyed. Most of all, I hope that you learned something great today, and I hope to see you again soon. So thanks for watching EEforEveryone, and thank you for staying till the end. Bye!